wait for 2 more minutes for others to join. Okay, we'll start. So I'll give you the interactive live session on week 2. So first I'll cover week 2 videos summary, and after that so along with that I'll discuss some of the simple questions on week 2 week 2 topics. So that will be helpful for you for the NSEM exam. But remember that the questions I'll discuss will be more easier one. So if you'll get the idea of those simple questions, you can answer much difficult questions. I think for NSEM you will have much difficult questions. Okay, so these questions will be helpful for you. Then after this presentation, I'll just give the summary of the assignment. Okay, how it can be done. Okay, so we'll go to the summary of week 2 videos. So the first topic sir discussed is hierarchy of geometric transformations. So we'll have two images with us, source image and so we'll have two images with us, source image and target image. Okay, so we can define different transformations between source image and target image. Okay, say if we have a square in this image, if the square is here, the transformation like this, we can say that some transformation can be applied to the source image to get the target image. So first of all, the first transformation is what? Simple translation. So if you have a square here, if it is transformed to another location here, then we can say that the square has some translation. So that is a simple translation. Next one is next transformation is simple in plane rotation. So that is similar to this square. Like if you have a square like this, it will have only a rotation, an in plane rotation. Okay, so that is the second transformation, in plane rotation. Then the third one is scaling. Scaling is like if you have source image and target image, then if you have a square in the image, then that will be scaled to a smaller square. So this type of transformation is scaling, third one. Okay, So these three are very simple transformation. First one is translation, second one is rotation, and third one is scale. Then as the fourth transformation, we have similarity transformation. Okay, similarity transformation, where we have three operations. First one is scaling, second one is rotation, and third one is a translation. So it is a combination of three transformations. Okay, then that transformation is known as similarity transformation. So say in an image we have source image and target image. If we have a square like this, after similarity transformation, after rotation, scaling, and translation, this square may be here with a scale. So this type of transformation is known as similarity transformation. Here we have how many unknowns? Scale is an unknown, right? Scale value means in the above equation we have a, so that is one unknown here. Then for the rotation matrix we have how many unknowns? For the rotation matrix we have one unknown, only theta is unknown, right? So for in R, theta is unknown. Then we have two translations, Tx and Ty. So in similarity transformation we have four unknowns: scale factor, rotation theta, then Tx and Ty. So we have four unknowns for similarity transformation. Then we have affine transformation. Okay, affine is more general. Like if you are multiplying this S and R, you will get one matrix, right? But that will have some zeros. But this ABCD matrix is a more general one, and this type of transformation is known as affine transformation. So for affine transformation, if we have a source image here and a target image here, then if we have a square like this, it won't be a simple rotation, but its angle will be distorted. Like if we have a square, then we'll get a parallelogram like this. Okay, so in the case of similarity transformation, angles and ratios of lengths are preserved. But in the case of affine transformation, parallel lines becomes parallel, but the angles won't be preserved. Okay, so these are the main transformations. So the new ones are similarity transformation and affine transformation. Okay, so just remember that for similarity transformation we have four unknowns. Then for affine transformation we have ABCD into XS, YS and TX, TY. So okay, so the first question: how many unknowns are there for similarity transformation and affine transformation? So I will launch question 1. If you can answer these questions, you can poll. Okay, otherwise you can give answers in chat box also. How many unknowns are there for similarity transformation and affine transformation? Option A 5 and 6, B 4 and 6, C 6 and 7. Okay, for translation, we have Tx and Ty only, right? For rotation only we have theta. For scaling we have S or A, scaling factor, right? Similarity is a combination of 3. So we will have 4 unknowns. Then for affine transformation, the equation is like this, right? A, B, C, D. So these 4 unknowns are there, along with the Tx, Ty are there. So we have 6 unknowns. Okay, so the answer is B 4 and 6.
Okay, then the next question, no, next, so why we are using homogeneous coordinates, that is the next topic. Okay, so a simple Cartesian coordinate x1 y1 has two elements, right? x1 and y1, x coordinate and y coordinate. When we are converting this Cartesian coordinate to homogeneous coordinates, it can be written like x1 y1 1. Okay, so if we have 5 10, then the homogeneous coordinates corresponding to 5 10 is 5 10 1. Okay, then this is equivalent to writing 10 20 2. Okay, so the thing is that we have to divide every x and y element with the z value. So we'll get what? 10 by 2, 20 by 2. So in homogeneous coordinates, 5 10 1 is equivalent to 10 22. So why we require these homogeneous coordinates? So that is why, because we are writing one transformation, we are writing a transformation between one coordinate in one image to one coordinate in the other image. So if we have to write a simple matrix multiplication, we have to write x1 y1 as x1 y1 1. So for writing transformations as a simple matrix multiplication, we require homogeneous coordinates. So in our previous case, we have a simple case we can take translation. How will you write? xt yt, xt is equal to x1 plus tx, yt is equal to y1 plus ty, right? So how can we represent as a matrix multiplication? We will write xt yt 1 is equal to 1 0 tx 0 1 ty 0 0 1 into x1 y1 1. Try to multiply 1 into x1 is x1, 0 into y1 0 plus tx into 1 tx. Then the next element is x1, x1 into 0, y1 plus ty, right? So if you are writing it as a matrix multiplication, we should require what? Homogeneous coordinates. So similarly we have rotation matrix also. For rotation also we have one transformation matrix. Cos theta minus sin theta 0, sin theta cos theta 0. So just multiply with cos theta x1 minus sin theta y1. So we will get the same equation as the previous these equations. First equation we got from the simple matrix multiplication. Okay, then consider this figure, this rabbit figure. Okay, so here most general transformation is given, so that is known as projective transformation. So in projective transformation, a simple rectangular shape won't become parallel, like that will be so here angles are not preserved, right? Angles are not preserved and the parallel lines won't be parallel after transformation. So this type of transformation is more general and can be represented as a matrix multiplication with matrix has 9 elements. Okay, h11 to h33. So this is a more general form and every transformation can be written using these 9 elements as given in the left side. Okay, and in this equation we are using homogeneous coordinates. So since the third element is a scaled element, okay, we can say that we can actually change the because if you are writing x1 y1 z1 here, if you are multiplying it with k value, then also the coordinate will be the same in homogeneous coordinates. So that will be equivalent to multiplying this k with this h matrix. K into h is also the same, right? So the scaling is done by ourselves. So So we can give a condition like sigma h should be some value k. Okay, so that is one constraint. So this constraint we can give. So even if it has 9 elements, the number of unknowns will be only 8. So this equation, since the last element is only a scaled value, this general projective transformation equation has 8 unknowns. Okay. So this is the main concept. Projective transformation matrix has 8 unknowns. Then this is the figure for perspective projection. It is a projection from 3D scene point. Okay, this is the 3D scene point. So this point is mapped to this point here on the sensor plane. Then we have a we have a relation between small, so the image coordinate, sensor plane coordinates will be small x and small y. Okay, 3D scene points are capital X, Y and Z. Okay, or D. These are Cartesian coordinates. So when we are converting that to homogeneous coordinates, it will become xy d1, and here it will become xy1, right? So we can relate this capital X and small x, capital X and small x, capital Y and small y, okay, using focal length f. Okay, how they are related? So the next question is about that relation. Find the image coordinate xy corresponding to the 3D scene point xyd 30, 60, 10 for a camera with focal length f equal to 5. So all the measurements are given in millimeter. Then if you know the answer, you can vote. Okay, I have launched the poll. You can answer. So from the figure itself we can find using similar triangles. So from the pinhole to this 3D point, the length is d. Then the height of that point is x. Then the height of the image coordinate is small x, and the distance from the pinhole to sensor plane is f. So using these 4 quantities you can find a relation and you can find the answer. Okay, this topic is already covered in the week 2 videos. Okay, I'll end the poll. You can answer in chat box also. Okay, so using the relation between x, y, so using similar triangles we can write okay, so, using the relation between x and y and focal length, we can write small x divided by focal length is equal to capital X divided by distance, that depth. Okay, then we'll get small x is equal to f into capital X divided by d. So we'll write small x is equal to capital X is what, 30 into f is 5 divided by d is 10. So we'll get 15. Then y is equal to capital Y into f divided by depth is equal to 30. So the answer is C, 15, 30. Okay, so it is a simple projection equation. The question 3 is very simple. Find the Cartesian coordinates corresponding to the homogeneous coordinates 10, 25. So I launch the poll, you can answer. So Cartesian coordinates will have two values. So what is the answer? The thing is that, so any value, like if you have 2, 3 coordinates, okay, you have 2, 3, so it is equivalent to, in homogeneous coordinates it is equivalent to 2, 3, 1. So that will be equivalent to 4, 6, 2. So if you are multiplying with a constant, it will be the same coordinate will be represented using different values. Okay, so the thing is that we have to multiply, we have to divide every values by the third z value. So that is the aim. So here we have 10, 25, right? So the Cartesian coordinate becomes 10 by 5, 20 by 5 is equal to what? 2, 4. So the answer is 2, 4. Okay. So the answer is 2, 4. So the Cartesian coordinate corresponding to the homogeneous coordinate is 2, 4. If the question is like this, if the Cartesian, find the homogeneous coordinate corresponding to 2, 4. So if that is the question, you can write it as, what is homogeneous coordinates? 2, 4, 1. Or you can select any option which is a which is the product of this 2, 4, 1 with values 2, 3, 4, 5, etc. So if the option has 4, 8, 2, you can select that option. Okay, so if the question is to find the homogeneous coordinates corresponding to this Cartesian coordinate 2, 4, you can either select 2, 4, 1, 4, 8, 2, or 6, 12, 3. Okay, so it won't matter if you are multiplying any constant value to the base homogeneous coordinate. Okay, so this is a simple question. Next thing is projective transformation. So here this topic is not that much simple. Here we have this plane. So these topics are already covered in the lecture. So it is better if you come after watching those videos, it will be very beneficial to you. Okay, because if you are listening for the first time, it will be very difficult if since I am explaining not that much deeper. I'll give some equations and all that will be that are already covered in the videos. Okay, so let us consider a plane here. So that's a 3D plane. Okay, so now we are considering only the planar world. We are not considering any depth and all. So if we are watching a scene very far away, we'll watch the scene as a plane. So that type of scenes are we are considering here. Okay, so consider a point P in a 3D plane like this. So that will be a 3D point. So that will have coordinates x, y, z. So in homogeneous coordinates it will be written as x, y, z, 1, right? So in projective transformation theory, every 3D x can be converted to an image coordinate. That is, we are capturing that 3D scene to a camera. Okay, so camera will have this image coordinate small x, but we have 3D coordinate capital X. So they will be related using matrix P. that matrix P is known as projection matrix. Okay, so normally if you know the camera matrix, K is the intrinsic camera matrix. So K depends on the focal length of the camera and it depends on the intrinsic parameters of the camera. Okay, so every camera will have different Ks. So if you know the K value of a particular camera that we are using to capture the scene, then its P matrix, if there are no rotations and all, we can represent that P as K into I is the identity matrix I0. Then P will be, this projection matrix will be K into I0. Okay. So here consider a point in the 3D plane is x1, y1, z1, 1. So point in the image plane is small x1, y1, z1. Okay, so that is in homogeneous coordinates. That can be represented using K and I0. Okay, K is K has so that is already explained in the videos. K has a form like focal length 0, principal point 0, focal length, principal point 0, 0, 1. So that is the general representation of intrinsic matrix of a camera. So so we can write the projection matrix as f0, 0, 0, f0, 0, 0, 1, then I0. So every 3D point can be transformed like this if you know the camera matrix. Okay. Then our aim is to find transformation between two planes. Okay. Two planes means two images. So here we have one image here, image 1. Here we have image 2. Okay. These image 1 and image 2 are captured using two camera setups. And we are interested to find a transformation between this image 1 and image 2. Okay. So that is our aim. But the point, the planar scene is the same. Okay. Then you can go through the videos and you can find that this is the image coordinate in camera 2, this is the image coordinate in camera 1. Okay, so they are related using a single transformation, right? So image 2 coordinate is equal to some transformation into image 1 coordinate. So we can write this transformation as K. K is the intrinsic camera matrix and R is the rotation, what amount of rotation we applied to the camera to get the second image. Okay, so that is R plus what amount of translation we apply to the camera for the second image. Then N is already explained in the video. N is the unit normal. Okay, so this is the unit normal. So if it is in the z axis, that will be 0, 0, 1. Okay, then divided by D. D is the distance from center to the C. Okay, depth into K inverse. So this is the transformation matrix equation. Okay, so so the next question is, so we can write it here. So the transformation equation is K into R plus T N transpose by D K inverse. Okay, and in the lectures sir explained different cases: in plane translation, in plane rotation and scaling. For each of those translations we have to find out T, R and T, R and N. Okay, so the question is, what are T translation matrix, rotation matrix and the unit normal in the case of in plane translation? So I'll start polling. I launch the poll, you can answer. What are T? Translation, rotation, and N, unit normal in the case of in-plane translation. So you can answer in chat box also. So okay. So what is in-plane translation? Say if we have a flower here in 3D, okay, we are capturing that 3D image using one camera here, C1 here, and we just translate that camera just rightwards, okay, to C2. So that is another camera orientation C2. Then we'll take the picture of that uh, flower, okay. So here translation metrics. So translation is only in plane. In plane will be towards this side, towards right or towards upward also, okay, not towards the flower, okay. So we have Tx motion and Ty motions are there, not a Tz motion, okay. So the translation metrics will be what? Tx, Ty, 0, and the unit normal will be along the z direction. So x and y will be along this image planes, and unit normal will be along the z axis. So n will be what? 0, 0, 1. Okay, if it is along the x axis, we will write 1, 0, 0. If it is along the y axis, we will write 0, 1, 0, but it is in the z axis. So the unit normal is 0, 0, 1, and rotation, we are not giving any rotation to the camera, so R will be I. So the answer is A. Question 4, answer is A. Then so in the lecture, sir explained 3D rotation metrics using angle axis representation. So R equal to e raised to s theta is what is written, where s is a matrix like this, okay, where ax, ay, az is the axis. So where ax, ay, az is the unit axis about which rotation is done, okay. So if it is an in-plane rotation, it will be x, y, z. So if it is an in-plane rotation, the rotation angle rotation is about the z axis, okay. So what is the expression for R using S? That is already derived in the classes. So can anyone answer question 5? So that is already discussed and derived, so I am not deriving here. Question 5. So I will give the answer. It is answer A. Okay. Then so this value, this R can be this I plus sin theta s plus 1 minus cos theta s square. This equation is used to find out the transformation. So that will do here. Okay. So next question, write R, N and T for in-plane rotation and scaling. So first we will take the case of in-plane rotation. Okay. So rotation means we have x axis, y axis and z axis here, right. So whether there will be any translation for in-plane rotation, we are not translating the camera. So this will be what? No translation, 0 0 0 0 0. Then rotation value will be e raised to s theta, right, where we can write s using ax, ay and az. Okay, so ax, ay, az is about which axis we are rotating? In plane rotation. So we are rotating about z axis. So s will be, some equation is there where ax, ay, az will be around z axis. So 0 0 1. So this values you have to substitute here, and you have to find out that value of r using the above option. Okay, so you will so you got r, t, r, then n. It is an in plane rotation, right? So the n value will be what? So the unit normal is along the z axis. So 0 0 0 0 1. Okay. Then in the case of scaling, whether there is any translation? No translation, right? So 0 0 0. No. So for scaling, we have to zoom in and zoom out. So we have to go towards the C. So we have to move towards this z axis for scaling. So we have one translation along TZ. Okay. Then R will be no rotation. So R will be identity matrix only. Then translation is TZ. Then N will be what? N will also be 0 0 1. Okay. So this is question 6. Then the next question, for a camera with focal length 10. So I have already explained the format of camera matrix, right? So you have to write the equation for K. So K is a matrix with 9 elements. So you are given focal length 10 and principal point 20 30, skew 0. You have to write the intrinsic camera matrix. So I have already given the equation in the first slides. Just write what is K. You have focal length 10, principal point 20 20. Principal point is the point given as P. It's a letter P here. Okay, so this is the what principal point. Skew is also given 0. So K will be K has the format fx 0 cx 0 fy cy 0 0 1. So skew is here. Okay, so fx is the focal length, fy is also the focal length, cx and cy are the principal point. So the answer is A, f0 cx 0 f cy 0 0 1. Next question, for a camera with focal length 10 and the principal point at 20 30 with skew 0, same as the previous question. Write the projection matrix of the camera and find the projection of the 3D point on the image plane. Okay, so you are given K, right? K is equal to 10 0 20 0 10 30 0 0 1, and you are given 3D coordinates. 3D coordinate is 10 20 10 1. In homogeneous coordinates we have to write, okay, for before multiply. Then you know the projection matrix. So you know the projection equation, small x is the coordinate at image plane is projection matrix into capital X. So what is projection matrix? K into I0 into X. So if there are a rotation and translation, instead of this I, we should write R and T. So that is already explained in the lectures. So you'll get what? 10, 0, 20, 0, 10, 30, 0, 0, 1, K into I0. I0 is 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0 into capital X. 10, 20, 10, 1. So what should be the answer? 10, 0, 20, 0, 10, 30, 0, 0, 1, 0, 0, 0 into 10, 20, 10, 1. So we'll get answer, right? 3 values you will get. And if you are finding Cartesian coordinates, you have to divide every x and y coordinate by the z coordinate. Okay, so I think the answer is 100 plus 200, 300. Next 200 plus 300, 500. Next is 10. So the answer is 300 by 300 by 10 is 30, 500 by 10 is 50. So in the assignments also you have to divide the homogeneous coordinates you got by divided by that z coordinate to get the image coordinate. Okay, so this is the question 8. Then comes homography. How many point correspondences are required to find the homography matrix H? So I have said that for a general projection transformation, you will have x is equal to x2 is equal to some h into x1. x1 is the coordinate in the image 1, x2 is the coordinate in the image 2. So those two coordinates are connected using a matrix with 9 values. Okay, so this is h. So you know x2 and x1. Okay, you know x2 and x1. You have source image and target image. You know x1 here and x2 here. Okay, some say if you have a flower here, so you know where is this point in source image and the same point in target image. So you know the correspondence points in source and target. So you know x2 and x1, same points. Okay, x2 and x1. Then you can find this h. How? So this h has how many unknowns? 8 unknowns. Okay, so this topic is already covered in the session. So 8 unknowns from 1 point correspondences. That is, if you have one set of x1 and x2, you can write 2 equations. Okay, but you have to solve for 8 unknowns. So 1 point correspondence give 2 equations. Then if you have to get 8 equations, if you have 8 equations only, you can solve for 8 unknowns, right? So you should get 8 equations. Then how many point correspondences will be required? So that is the 9th question. I'll launch the poll. If someone can answer. Using 1 point correspondences, you will get 2 equations, but you need 8 equations. Then how many point correspondence are required? Okay, so the answer is 4. So using 4 4 point correspondence means you should know the center point of this flower, then you should know some other point on the two images, then you should know some other point in the image. Okay, then other point also. So if you know 4 points, 4 set of correspondence points, you can find the homography matrix H. So this is also in one assignment. So what is ransack? Ransack algorithm is already explained in the lectures. So from two images, source image and target image, we have 4 point correspondences. Using 4 point correspondences, you can get H, right? But how can we select those 4 point correspondences? It is not easy to select any such random point, right? So some of the algorithms are already there to return this 4 point correspondences using shift, surf, etc. So if you are using a shift operator on these two images, that shift operator will give you these 2 points are correspondence points, these 2 points are correspondence points, these 2 points are correspondence points. So if you run the shift operator on these two images, it will give you 1,000 of points. Okay, but we can't trust that shift operator. So say you have 100 point correspondences returned by shift. Okay, but we won't trust the shift. So we'll first take 4 point correspondences. We'll take any 4 point correspondences from this 100 set. Using that 4 point correspondences, you will find what H. But you are not sure you took the correct 4 point correspondences. In some cases shift may return bad values. Okay, bad point correspondences. Okay, so you just randomly took 4 point correspondences, and from 4 point correspondences you found H, but you don't trust that H. So here you have x1, here you have x2. So after finding H, you will just transform this x1 to some x2 dash. Okay, so every x1 is transformed to some x2. Then x2 can be the same x2 shift returned, but it may not be the same. Then you will find the difference between x2 and x2 dash. If the error is less, you will make them as a consensus set. Consensus set is the set of coordinates which agrees this H, okay, which obeys this H. So you are getting, out of 100 points, you are getting 90 points which obey this H. Okay, so you can say that this H is good. But if you are taking wrong 4 points, then it will return wrong H. It will return wrong H. Then if you are doing this transformation and if you are finding this error will be very high. So consensus set won't be have that much points. It will have only 50 points that obey this H. So we can't accept that H. So we should accept a particular H that will have maximum number of points in the consensus set. So that is the algorithm, ransack algorithm. So in iterations, we'll again take different 4 points and find H and find the consensus set, and we'll see whether the consensus set has enough points. Then only we'll accept that H. Okay. So H is founded by using shift. Shift will return more points. We'll take any 4 points and find H. And find the transformation and find the error. If the error is less, we'll make those points as consensus set. If the consensus set is having much values, we'll accept that H. That is the ransack algorithm. So this will be used in the next assignment. So the topics are already over. Next I will discuss the lab assignment 2. Okay, so okay, so in lab assignment 2 you are given two images, image 1 and image 2. So you have to find out the transformation from one image to the other. So as a first observation, we can say that some rotation is there between the image 1 and image 2, right? And there is some translation also. And the question itself, it is given that translation is there and rotation is there. Not an affine type of transformation is there, right? You can see that one plane is here and one is here, but this plane is extra. So you have to just translate this the second image to this type only in the orientation of the first image, so that if you are finding the difference between this and this, you should get a plane here. Okay, that small plane should be here. So that is the aim. So you have to find out the transformation. You have to transform the image 2 in the orientation of image 1. So in the question itself, you are given 4 point correspondences. No, 2 point correspondences are given. So how will you find the using 2 point correspondences? You have to find a translation and rotation. So your matrix transformation matrix T can be written as what? Cos theta sin theta minus sin theta cos theta tx ty 0 0 1. So the number of unknowns is only tx, ty and theta. 3 unknowns are there, right? So from 1 point correspondences you have you can solve 2 unknowns. So for 3 unknowns you have to have 2 point correspondences. So those 2 point correspondences already are given in the question. So it is given that here the value is 100 200. The same point here is 150 200. Okay, so this is 1 point correspondences. Then the next point correspondence is 50 150 is here, and here 200 100. Okay, so these so this is not the exact values. These values are already given in the question itself. So you can write okay, I'll just write quickly. So you can write xt is equal to cos theta sin theta minus sin theta cos theta xs ys, okay, plus tx ty. So xt is equal to cos theta xs plus sin theta ys plus tx. Yt is equal to minus sin theta xs plus cos theta ys plus ty. Then you can name this cos theta as a, sin theta as b, tx as c. So here it is minus b, here it is a itself, here it is d. So you can write a xs plus b ys plus c is equal to minus b xs plus a ys plus d. So we have 4 unknowns, right? So you can write xt yt as xs1 ys1 1 0 ys1 minus xs1 0 1 and a b c d. So in order to solve 4 unknowns, you have to use 2 points, xt2 yt2 xs2 ys2 1 0 ys2 minus xs2 0 1. Okay, so these two matrices are already you have in the question itself. xt1 yt1 xs1 ys1 all values are given. So you have to write this B matrix and this A matrix, then solve for this X matrix. Okay, so you will get A, B, C and D, right? Then you know cos theta, sin theta. Cos theta is A, sin theta is B, and tx dy C and D. So you have to first find this A, B, C and D, then write T as A, B, C minus B, A, D 0, 0, 1, then source image and translation matrix. You have to translate source image to target image and just find the difference between the source image and target image. Not source image, the first image and the target image. So you need not use those two images. You are already given the point correspondences. Using those point correspondences, find A and B. Okay, this A and small b, find X, A, B, C, D, then find the transformation matrix. Then using transformation matrix and source image, just find the target image. Just do the difference between the first image and this target image. That's all. So you have to use the target to source transformation in order to avoid holes. So this is the assignment 2. So that's all about today's session. So do you have any questions? So this YouTube link and the link for this presentations will be shared with you. So do you have that link for the first week? Did you get? Okay, if it is not shared, it will be shared. Okay, so submit all the assignments in time. It will be beneficial to you. So you have to fill in codes, okay, and you have to run. That's all. Okay, then if there are no any other questions, we can stop here. Thank you.